Okay, section 11.3 is about testing claims about two means, just like section 11.2, but now we have independent samples. So instead of just one sample and measuring two different readings from the same sample, we're going to have two populations. So population 1 and population 2, and then from each independent population, we're going to take a sample from each group. And these two groups are not linked in any way. It's not the same subjects with a before and an after. And this section is about testing means, and so we're going to be dealing with numerical data. And as soon as you're dealing with numerical data, you know that the way we analyze numerical data, partly, is with a mean. And so what you're going to have to write down for each of these groups is the first mean, the second mean, and the sample size, the first sample size. And as before, we're going to give these subscripts. And then we're going to go over to the other population and calculate the mean and the standard deviation and the sample size of the next group. And to determine if there's a difference between these two groups, we're looking at the difference in the mean. So we should always report these summary statistics because it's those two, those means. If there's a big difference between them, then you can expect to see a statistically significant difference in the two population means. If there's not a big difference between those two sample means, then probably there's not going to be a statistically significant difference in the two groups. So we want to compare two groups all the time. And you'll see a sampling of some of those problems. But here are the summary statistics that you want to and how the test is set up. All right, so let's go through the 5 steps of this test, just kind of a broad outline, and then we'll go into some specific problems. So the first step is always to write the hypotheses. And, as before, be sure to define the variables that you use in your hypotheses. There are always 2 hypotheses. One of them is the research claim, usually the alternative hypothesis. They are competing hypotheses. What's nice about this section, just like 11.1, is that the statement that there's no difference in the means is mu1 equals mu2, and regardless of the test type, one-tailed left, one-tailed type, or one-tailed right, or two-tailed test, the null hypothesis will always be the same. And so we're comparing two population means. The null hypothesis is a statement that the two means are the same. The research hypothesis is going to involve the not equal to, the less than, or the greater than. And then you'll want to be sure to define both of those means. The population mean of the first group, the population mean of the second group, and say it in context. We do have a one-tailed left and a one-tailed right and a two-tailed test, but we're not going to use those here. And the reason for that is the degrees of freedom is based on a calculation, and I suppose we could use inverse t to find the critical value, but the critical values are not going to appear in the table because the formula for the degrees of freedom involves this messy thing, degrees of freedom. It involves variances divided by sample sizes of the two groups. You're adding them together, squaring it, and then you've got, this very complicated fraction. So it only uses the standard deviations in the sample sizes to calculate the degrees of freedom, but the formula is just very messy. Seems like a lot of work just to do the classical approach. So what we're going to do in this section is we're either going to use the p-value approach. So I'll just say no classical approach. There is one, but we're just not going to use it. So that means we're left with the p-value approach or the confidence interval approach. Generally, the degrees of freedom, if you want it, is going to be something like, it's going to be like n1 plus n2 minus 2, something like that. It's going to be close to that. And we'll check it a couple of times. But this is not equal to, so don't write equal to. It's approximately equal to this. But as you would expect from a very complicated formula, that involves a fraction, that usually this is not going to work out to a whole number, like 14, so that we could go use a table and it's going to be 14.1796 or something like that. Okay, step 2, level of significance. There's no difference in how we've been identifying this level of significance from what we've done in the past. That number, 0.05, 0.01, a small number, 0.10, probability of making a type 1 error, rejecting the null hypothesis when in fact it's false, or when in fact it's true. We want that probability to be low. Okay, step 3. This is the step we're going to be primarily using the confidence interval, or most of the time we'll just be using the p-value approach. So the calculator function that we're going to use to get the test statistic and the p-value. All right, so we have two means, and the way that it appears is the two sample. And it turns out the distribution we're going to use is the t-distribution, and then t-test. Now, because you're using numerical data, you can actually put that numerical data into L1 for the first group, and put the numerical data for L2 into the second list. So you could work two lists. So it's always going to ask you for the input. So it'll be one of two ways. And you will have some problems where they do give you the raw data for the first group, and they give you the raw numerical data for the second group. And if that is the case, then you'll want to put those data values into L1 and L2. All right, if you use the summary statistics, then you have to give X1 bar, S1, and N1, X2 bar, S2, and N2. So you have to type in those 6 values we identified here that you have to provide. The null hypothesis is always the same. It's the alternative hypothesis that changes the sign there. And so therefore, we don't have to tell the calculator anything about the null hypothesis because it knows it's going to look like this. So there's nothing that comes before that. But you do have to say something about the H1. And so you have to indicate not equal to, and this might just be a colon here, not equal to mu2, greater than mu2, or less than mu2. And you have to select one of those options. All right, so that's what you would have to enter in if you're going to use the stats option. And if you're going to use the data option, you just have to tell the calculator, I don't know if it has X1 list or an X2 list. I'm not sure what it is, but it's going to ask you for 2 different lists. And you would put those lists into L1 and L2. Again, there's no need to do anything with the null hypothesis. And if you give it the raw data, it can calculate X1, S1, and N1, X bar 2, S2, and N2. So that's all it needs. So the only other thing, there's one other thing. There's a couple of tests, and I think it's probably going to be over in this one too, pooled. And they give you an option of yes or no. We're always going to select no. We're not going to pool the variances here. We're not going to make any special assumptions about the populations here. So if you select no, then your results will be consistent with the way that we're doing things here. So that will come up in either of the 2 versions, yes or no. So always select no. And then as before, you have to say something about the alternative hypothesis. Mu1 equals, or mu1 not equal to mu2, less than mu2, or greater than mu2. And you have to select one of those. All right, so this will get you the test statistic and the p-value. The test statistic that we're going to be using is a t. Our author calls it t sub 0, is the test statistic. And under certain circumstances, we have x1 bar minus x2 bar. If there's a big difference between those 2 sample means, then that would force the numerator of our fraction, our test statistic, to be large, which would in turn increase the size of the test statistic. So what we're doing is we're calculating a test statistic based on the differences in the means. And then we subtract the population means. And because our null hypothesis is mu1 equals mu2, we're going to assume this to be true. When we subtract mu1 minus mu2, this whole piece is equal to 0. So usually it just doesn't appear. And it turns out that the sampling distribution for a difference in two independent means like this, the standard error term down here is the variance divided by the variance of the first sample divided by the sample size, and then same adding that to the variance or the square of the standard deviation of the second group divided by the sample size. And the way to remember this is if you just took the square root of this piece here, the square root of S1 squared would be S1, and the square root of N1 would be the square root of N1. So you'd have S1 divided by the square root of N1, which is the standard error in the single sample case. But then we're adding them together. But anyways, that's the formula that we probably won't do a whole lot with in terms of using it to calculate the test statistic, but the calculator does this work behind the scenes, and it's just going to report out the test statistic and the p-value if you use this function. Okay, so moving ahead then, step 4 is to make the decision, and there's no difference in how we make the decision here. We're either going to reject the null hypothesis if p is less than alpha, and do not reject the null hypothesis if p is greater than or equal to. And then you have the conclusion. And this is where you make a final statement that describes what the data shows evidence for, or shows no evidence for. We call this interpreting the decision. Okay, so same 5 steps, and we'll do a hypothesis test now, and then we'll go ahead and do a confidence interval problem as well. All right, so from the notes, you can see here that I have some notes for you to check out afterwards. We're testing hypotheses regarding the difference of two means from independent samples. We want our sample sizes to be larger than 30. We have two-tailed, left-tailed, right-tailed test. Notice that the null hypothesis is the same regardless of the test. And the only difference in the tests would be the sign and the alternative. The calculator will calculate the degrees of freedom for us. It's going to be approximately equal to N1 plus N2 minus 2, or it's going to be close to the max of N1 minus 1 or N2 minus 1. So it's going to be in that range, and we'll come back and check it once we have done a couple of problems. All right, calculator. For the TI-84, we're going to use the 2-sample t-test, and later on when we do a confidence interval, we're going to do the 2-sample t-int. And those are all in the same menu, the test menu of the calculator. Okay, let's take a look at an example. Walking in the airport. Do people walk faster when they're departing an airport, getting on the plane? Do they walk faster to their plane? Or when they are arriving, when they're getting off the plane, do they walk faster? Now, if I just have to use my own experience, I usually get to the airport much earlier than I need to, so there's no need for me to run to my gate. So I'm just kind of casually walking to my gate. However, when I get off the plane and I'm going to my car, the sooner I get down to the taxi, the faster I'll get to my car. So I tend to walk faster after I get off the plane. Let's see if these results are consistent. And this was data collected in San Francisco and Cleveland airports. There they are. All right, so I'm going to call this population 1 and this population 2. And so if we just use our variables, the mean is x bar. So x bar 1 is feet per minute. So they're talking about speeds here, 260 feet per minute. And x2 bar would be 269. So just like me, it looks like they're going a little faster after they arrive, and they're going on trying to go get their bag or whatever. Standard deviations, these are S1 and S2. And then the sample sizes, N1 and N2. Okay, so a researcher measured the walking speed of travelers. Do people walk faster when they are departing or when they're arriving? So there's no indication that it's faster one way or the other. So let's write the hypotheses that the means are the same. And since in the original question posed that they're not specifying if one is faster than the other, this turns out to be a two-tailed test. Now, the way that the question is phrased, I suppose you can put the claim either place. I'm thinking that it goes here because they're indicating from their question that there is a difference. They just don't know what it is. Mu1 equals the mean speed walking upon arrival, or mean 2 is the mean speed walking upon departure, or something along those lines. All right, two-tailed test, the not equal to, the level of significance. I don't see it anywhere in the problem, so I'm going to specify alpha to be 0.05. And now I'm going to enter in the summary statistics into the calculator function and run the test, find the test statistic and the p-value. All right, so we go over to test and then down, notice there's 2, number 3 and 4 look very close. And we want to do a t-test. All right, I don't have the raw data. I don't have, of these 35 individuals, I don't have their individual speeds. I just have the summary statistics. So I have to go select the stats and hit enter. And then I'm going to enter in these 6 numbers: 260, 53, and 35. Sample size is larger than 30. 269, 34, and 35. I have to select the not equal to as the sign. And then here's that pooled equals no business. So just make sure that this is always selected no. So, and then we're going to calculate, and this is going to give us, as it always does, the test statistic and the p-value. All right, so it indicates here the test that you claimed, test statistic, p-value. So let me write those two down. All right, and I'll round it to 3 decimal places, test statistic and the p-value. Look at the degrees of freedom. See how it's not a whole number? So let me just write this one down here. So if we use this n1 plus n2 minus 2, you can see that n1 and n2 are both 35. And so if you take 70 minus 2, you get 78. Well, that doesn't seem to work very well here. No, 68. 70 minus 2, 68. All right, so it's still a ways off. But we have enough. We can see that we are going to not reject the null hypothesis since p, which is 0.401, is greater than alpha, which is 0.05. Okay, now the claim is the alternative, and we were unable to reject the null hypothesis and support the claim. So that's what we're going to say. There is not enough evidence to support the claim. I should say or slower, faster or slower upon departure or arrival, or some other verbiage that would work there. We see a difference. We do see that when passengers arrive, they tend to walk a little faster than on their way to the plane to get on. But that average that we observed, we would say, is not statistically significant. It could have been caused just by the random sampling variation of the subjects we used. All right, so there are the 5 steps. Now let's go to 1, where instead of putting in the summary stats, let's use one where we actually enter in the raw data. All right, the only difference here from section 11.2 is that you're not going to create a third list and subtract the L1s and the L2s. You're just going to use the L1s and the L2s. All right, so here's your second example, and this one is related to bacteria in hospital carpeting. They want to determine if carpeted rooms contain more bacteria than uncarpeted rooms. So to determine the amount of bacteria in a room, researchers pumped the air from the room over a petri dish at the rate of 1 cubic foot per minute for 8 carpeted rooms, and then did the same thing for 8 uncarpeted rooms. And then measured the bacteria in the petri dishes. Counted them up, and this is what they found. Do carpeted rooms have more bacteria than uncarpeted rooms? At alpha equal 0.05. Okay, so the first thing we're going to do is we're going to enter these data into two lists. All right, so clearing out my lists. And then I'm going to put these carpeted rooms, going to be in L1. And in this case, you don't have to have the same number of data values in the two different groups. When you're subtracting them in 11.2, you have to have the same number, but in this one, you don't have to. They just chose to have the same number of rooms. All right, so first get the data values in there, and there's you can do calculate the one variable statistics with the first list, 11.2. I'll just write that down. And notice that these are rates in bacteria per cubic feet. Okay, and then if you do the same thing and you do the L2, you get 9.7875. So you could go ahead and calculate those. Let me show you a new function. If you go to stat and then calculate, there's option number 2 is the two variable statistics. So if you tell it the two lists, it'll give you the mean, standard deviation, and sample size of both lists at the same time, and you can scroll through. All right, so you do have to specify the two lists, L1 and L2. If it asks for a frequency, just say 1, and then here you see the 11.2. I'm going to write down the standard deviation and the sample size, and notice that there's more down there. So if you scroll down, it gives you the second list in terms of the Y's. So you can see our 9.78. You don't have to use this function, but it's there. I'm going to write down the standard deviation and the sample size of the next group, and that would be SY here. All right, so here are the summary statistics. You'll want to do that for every one of these that you do. You always want to calculate the summary statistics, and we're comparing means, population means. So the best way that we can compare population means is to look at the sample means. And you can see that there's a difference. There appears to be less bacteria in the uncarpeted rooms than in the carpeted rooms. So we see this difference, but in order for us to have a statistically significant difference, there has to be a big gap between these. And we really don't know looking at them. We have some very small sample sizes, so maybe this gap that we observe is not going to be statistically significant. All right, so we have alpha equals 0.05. Let's go through the test. Mu1 is equal to mu2. That null hypothesis is always the same when we're comparing two population means, independent means. And then we have to decide, whether we have a greater than, a less than. And so I'm calling my mu1 the carpeted and then mu2 the uncarpeted. And if you go right back here, it's kind of subtle, but researchers want to determine if carpeted rooms contain more bacteria. So here's our carpeted rooms. That's our first group. If on average it contains more bacteria, then mu1 would be greater than mu2, and that's the claim. You can also see it down here. Do carpeted rooms have more bacteria than our uncarpeted rooms? So we turn that question around into a statement and just say carpeted rooms have more bacteria than uncarpeted rooms on average. So the means, when you define them, start with the word mean, because that's what they are. Mean bacteria per square foot, cubic foot in uncarpeted. Okay, so we've got the hypotheses, we've got the level of significance. Now let's go calculate the test statistic and the p-value. So we're going to go run the tests, and this is a 2-sample t-test, number 4. This time we're going to use the data. I put the list 1 data in L1, list 2 data in L2, and the frequency for each of those 8 data values in each list is 1. In our alternative hypothesis, we have greater than mu2. So I'm going to go change this to greater than mu2. Pooled will always be no, and then we calculate. So we get a test statistic equal to 0.956 and a p-value equal to 0.178. These are the first two numbers. They do report back the test that we selected. Degrees of freedom, 13.5. If you add 8 and 8, it's 16. 16 minus 2 is 14. Well, it's pretty close to 14. All right, and so I didn't really have to do all of this work beforehand because the calculator will calculate the mean and the standard deviation and the sample size of each of the two groups. P is greater than alpha, so do not reject the null hypothesis. So we're unable to show evidence of the research hypothesis is that there's more bacteria in carpeted rooms than there is in uncarpeted rooms. So there was a very small sample size here. And if you do have small sample sizes, notice they were very careful to say that these data are normal. And if you're selecting from normal populations, then you can run this test. And there are no outliers. So you need to know something about the populations, that they're normal, or you need to have large enough sample sizes. In the previous example where we had 35 and 35, those sample sizes were larger than 30, so we were good. In this case, they tell us that the data are approximately normal, and so we can use the t-test here. There is not enough evidence to support the claim that on average there is more bacteria in carpeted rooms. Okay, so one example with the summary statistics provided, and then another example where we have the raw data where we entered into lists. So those are the two hypothesis tests that you're going to see. And the last example I want to do is one that involves confidence intervals. So I guess I forgot to put these handouts in e-learning, so I'll put them in after class. Here's the confidence interval for the difference of two means. Now, I realize that this is the third time I've given you this, what I'm about to show you, but this is from section 11.3. I think if we go through it again, it'll kind of add to your understanding of what we've done before. So a confidence interval to estimate mu1 minus mu2. So we're trying to estimate something about two populations. In this case, it's the difference in their population means. All right, so if the confidence interval looks like, and we have three scenarios, a negative number on the lower bound and a negative number on the upper bound. That's the first scenario. The second scenario is that we could have our interval with a lower bound that's positive and an upper bound that's positive. And the third scenario is if we have a lower bound negative and an upper bound positive. This means that, all right, since we're estimating mu1 minus mu2, what we would be saying from this confidence interval, that this thing we're estimating, mu1 minus mu2, we're 95% confident or 99% confident, whatever the confidence level is, that the difference of these two falls in this interval. And since every number in this interval is negative, we would be saying that mu1 minus mu2 is negative. We're 95% confident of that. Mathematically, the way we write that is mu1 minus mu2 is less than 0. Negative means less than 0 in math. And then if you add mu2 to both sides, you can be specific and actually identify which mean is less than the other. In this case, mu1 is less than mu2. And if you're using this to make the decision in a hypothesis test, then you could say this gives support to, and the only hypothesis where we're going to see the less than sign, mu1 minus mu2, is in the alternative hypothesis. All right, the rest of these cases are similar. If both of the numbers of the interval are positive, then what we're saying is that when we estimate the difference in the means, we're 95% confident that this difference is in this interval, which means it's positive. Mathematically, we would write it mu1 minus mu2 is greater than 0. Numbers greater than 0 are positive. And then if you add mu2 to both sides, you get that mu1 is greater than mu2. Again, the only place that you're going to see the greater than sign, if we're talking about hypotheses, will be in the alternative. So this gives support to also mu1, H1, the alternative hypothesis. Okay, and then the third scenario is that if we're estimating mu1 and mu2, and we say that we're 95% confident that the difference is in this interval. Here we have a negative number, here we have a positive number. So zero's in there somewhere. We don't know where. Could be over here, could be over here, but somewhere in the interval. Zero's in the interval. So we'd say mu1 minus mu2 could be 0. It's plausible based on our results. In math, we would say mu1 minus mu2 could be equal to 0. And if you, as before, add mu2 to both sides, you get mu1 is equal to mu2. And because of the equal sign, that's going to appear, this one's going to appear in the null hypothesis. So if it gives support to anything, it would be to the null hypothesis. Right? So again, it's somewhat confusing because you're not just estimating a single population mean, but what you're doing is you're estimating the difference between two means. All right, let's look at an example. And the calculator function that we're going to use, instead of doing it by hand, and this is what you would have to do if you wanted to do it by hand, but we're going to use the two sample. It's going to be a t-distribution, and then it's going to be a confidence interval. So the function looks very similar. The inputs that you type into the calculator are going to be similar to what you type in for the two sample t test, but you do have to specify a C level, and they're not going to ask you any information about an alternative hypothesis. Okay, kids and leisure. Young children require a lot of time, and this time commitment cuts into a parent's leisure time. No, it's not more true than it is now for parents out there who have kids at home and they have to kind of monitor their online teaching. A sociologist wants to estimate the difference. Estimate the difference in the means. That's a confidence interval. A daily leisure time in hours, the adults who do not have children with those who do have children under the age of 18, children living at home. So a random sample, okay, so I'll say children at home, no children. So those are our two groups. A random sample of 40 adults with no children, okay, so no children under the age of 18 years results in a mean daily leisure time of, that's x2 bar is 5.62, 6.5 hours of leisure time with a standard deviation of 2.43 hours. I'm just kind of picking up these numbers right from the problem. And then they go on to describe the other group, random sample, once again, 40, which, that do have children under the age of 18. Results in a mean of 4.10, say about an hour and a half less leisure time, with a standard deviation of 1.82. All right, so construct and interpret a 90% confidence interval for the mean difference in leisure time between adults with no children and adults with children. So the last thing I want you to do today is to enter your confidence interval into the chat. So it's the two sample t int, two sample t int, two sample t int. The summary statistics, because that's what we have. Notice that the pooled version is still there, so make sure that that's no. C level 0.90, 0.9, and then calculate. And here's the example where we have both negative numbers. And so that means when we subtract mu1 minus mu2, it's negative. So that's evidence that mu1 is less than mu2. And that gives support for the alternative. So mu1 minus mu2 negative. So that means mu1 is less than mu2. Okay, we're out of time, so we'll stop. But you want to go on and interpret. Remember, to interpret, you have to say, we are 90% confident that on average, parents that have children at home have less leisure time.